basically applicator commissioning and QA. So what we'll go into as far as the different steps is what is outlined here. So inventory and visual inspection of applicators, functional tests, imaging tests, autoradiographs and determination of offsets, coupling of your applicators to transfer guide tubes, the treatment planning parameters that associated with each applicator, use of applicators with template libraries, and as far as the delivery goes, delivery verification of applicator plans, dosimetric tests, and associated training that goes into it, which is quite important, training of associated staff, and developing a program, an annual QA program that will follow up on the commissioning that initially is done. So there are a number of guidelines that you can look into for the applicator QA and commissioning. One useful report is APM task group number 56, which is the code of practice in brachytherapy physics. And if you look at some of the tables there, they do have the suggestions, guidelines on applicator QA. So, for example, here on the left, there are guidelines for interstitial applicators, and on the right, intracavitary. Since this is a busy slide, I'm going to break this down, and we're going to go step by step on going over each of the different components of this table and how would one go about implementing this in reality for commissioning. So once you have an applicator system, the first thing you want to do as far as your commissioning goes is to do an inventory of all the parts. And these applicators, as you see here, can contain a large number of parts that have to be assembled together, and there's a chance of there's missing components, and one wants to get an inventory at the start of what there is and what there isn't. So first step is to create an inventory log for all the applicators using an Excel sheet. You want the model, serial number, number of parts for each applicator. You want to gather any reference documents from the manufacturer, which can be quite helpful in getting the technical aspects of the applicator. So any technical diagrams would be very helpful. You want a list of applicator components. And in addition to these, usually what you can get from the manufacturer is sterilization instructions, which will be important when we come up with the policies and procedures for the applicators. For each applicator, you want to verify that you have the correct model, correct components, cross-check this with the manufacturer specs, and identify any missing components, and if those missing components will affect the applicator assembly and such. And once you do this, you create a log of each applicator you have, and this log will be something that you will refer back to in your annual QA. So it's important to develop this. Now, once you have the log of it, you want to start the commissioning process. The first thing is a visual inspection. And by visual inspection, we just don't mean look at it. What we're looking for is specific things. So first thing is you want to assess the applicator components for any damage or issues with structural integrity. So you're looking at structural defects, maybe hairline fractures. For needles, for example, you want to look at the sharpness, straightness, and for other applicators, you want to look at the integrity of each of the components. You can look at also the waterproofness by putting the applicator in a water bath and seeing if there's any leakage there. Overall, you just want to make sure that the applicator is in a condition that can be used. And this is important if you're getting applicators that have been donated from other locations and you don't know exactly what's going on with them. So once that's verified, you want to start documenting, as the TG reports suggest, the dimensions and the physical attributes of your applicator. So you want to make sure, for example, if you've ordered a cylinder, it's supposed to be 3 cm diameter. You want to check those dimensions. So basically, you want to do measurements that you have the correct diameter and length. And so, for example, diameter of cylinder, you want to check if you have need or the external lengths. And we will go into this in a little bit, but we will also look into what we have as far as the connection to the afterloader, i.e. the transfer guide tube, and what is the internal channel lengths that one would expect from that, which we'll touch base in a little bit later. But we would also like to know that we have the transfer guide tubes that are appropriate for the applicator to connect to the afterloader. At this time, you want to record the measurements that you have as far as the applicator dimensions go for future reference. Now, we get to the functional test, and this is quite important. The first thing you want to see is verify that the applicator can be assembled as intended. In addition to that, most applicators have different ways that they can be assembled. For example, different diameter cylinders, different size ovoids for your tandem and ovoids, and you need to check that each mode of delivery can be assembled properly. And you want to check the robustness and functionality of the assembled. So here we have, for example, a segmented cylinder. In the small portion on the bottom there is this lock. And we've had issues where the lock may not be functioning properly. And in that case, it could lead to the segments basically deviating or the system falling apart. So that's something that you would want to check the robustness of. Now, as mentioned, you want to check connectivity to the transfer guide tube. So for the image you see, for example, in the cylinder, you want to make sure your transfer guide tubes appropriately attached to that, to each individual channel. And then once this is done, I think an easy test is that you take a wire and send it through the assembled applicator. And this will give you an idea if there's any resistance or obstruction in the channels that you have to further investigate. In addition to this, obviously, we'll do delivery tests where the afterloader source and dummy wire is sent through, but this is a good initial step to just make sure that there is no resistance or obstructions in the applicator. As far as structural defects, it's very useful to do a radiograph because you can look at the internal structures, look for cracks, look for things that may be different for the same set of applicators that would indicate some sort of a manufacturing defect. Now, this can be done with an OBI system, for example, on a LINAC, if that's possible. Sometimes it's hard if you do not have a simulator to do KV imaging, but certainly a radiograph is fine. And also you can take a CT as well if you have access to that. Here, for example, is an example, the CT that one would take, and you can see here that we have the different components laid out, and with the digital ruler, we make measurements of external and internal lengths to confirm that they are in spec with what we were supposed to get from the manufacturer. One can also do measurement of the Hounsfield units. These are supposed to be, most applicators, pseudo water equivalent. Obviously, you don't actually get Hounsfield units of 0, but it's good to have a documentation of this prior to starting out as far as water equivalence goes. So as you know, most of the dose calculation in brachytherapy is done with TG43, which assumes that everything in the universe is a semi-infinite water with no inhomogeneity correction. So in some sense that it's good to make sure that we have something that's water equivalent or that can be um, ignored during the treatment planning process if we're using TG43. Now, as far as the imaging tests go, in addition to looking at any structural defects, there's a number of things that one can attain from it. So one important aspect is when you image an applicator or the applicator is inside the patient and you do a CT scan, you need to digitize the internal lumen of each channel of the applicator. And to do this, one needs to know where to put the tip of a specific channel. And to do this, one has to determine the dead space typically that represents the tip of the applicator to the distal point of the internal lumen. So in this case, we see a cylinder here. And during the commissioning process, what has been done is we've taken a CT of it with a dummy inside, and then we determine how much this offset, how much is this distance from the tip of the applicator to the distal point of the lumen is, and that will give us our dead space, and that will be used in the treatment planning process to indicate where your digitized channel goes to. And usually you have technical diagrams from the manufacturer and you confirm that it is indeed what is indicated in the technical diagram. So here, for example, we have a cylinder that's 3 cm. We actually usually measure this to be 3 millimeter dead space on top. Obviously, each cylinder that you have, each applicator you have, may be different. So for each applicator, you need to figure out that dead space so you can do proper CT-based planning. These are examples of CT scans of a tandem, ovoid, and a ring where you're looking at digitizing the dead space, which can be just done with a ruler if you can visualize the internal lumen. Now, more importantly, in the commissioning process, one has to measure the accuracy of the positioning of the wire within the applicator. To do that, what we typically do is measure the offset from, let's say, the tip of the applicator to the center of the radiation at a given location, at a given intended location. So if you look at this diagram here, the blue represents a applicator that you have. The wire represents the wire that you're using in your afterloader. Just a note of caution, obviously, with different applicators, there are different wire designs, and the specific values that are given here may not be what you will see in your system. There's a good description of each of the wires in the 2012 release of the high energy brachytherapy report, and that's where this diagram is from. But what we're trying to get from this image is that the program position, which is the tip of the wire, is at this location. So you can say, let's say you program it to be 1 cm from the tip of the applicator, or 1 cm from the inner distal end of the lumen. Now, what you want to measure, or what you can measure on a radiograph, is the center of the radiation. That's where it's distinguishable. And what we want to, based on the geometry of the source, what we want to know is, if we program it to go to this position, what is this offset, the tip to the center of the rotation, to the center of the wire? So in this wire, we have a 1 millimeter cap and 2 92 seeds, each of them being 2.5 millimeters. So we know from the tip, or the program position, to the center of the radiation should be 3.5 millimeters based on this value. And you'll see that in many of the examples here, we'll use that value to to basically get the distance from the program position and to determine the offset. So the offset is measured using an autoradiograph, and you compare that with a nominal offset, which would be from this program position. Plus or minus millimeter is acceptable. Greater offset should be investigated. Depending on the applicator, if you have a large offset, the applicator may be defective and you would return that. However, there are also applicators which are more complicated to commission, such as the ring applicators, where they may have a systematic offset. And this offset can be taken into account during the treatment planning process or the delivery process. And it's extremely important that at the time of commissioning, one determines this offset, sees if it's in line. If it's not in line, how are you going to incorporate that in your planning and delivery process? So as an example, here just the autoradiographs and offsets for interstitial needles. Here are stainless steel needles. These needles have a dead space when you look at the manufacturer spec of 4 millimeters and a trocar tip. And this is where the lumen, I don't know if you can see my mouse, where the lumen starts. So in this case, we have sent the source to different positions, different starting positions. So it's kind of faint that you can see here. This was a double exposure where you can see the tip of the applicator, which is the dead space, and then a sequence of duals that we've sent the radioactive source in. And here you have different values because we're testing different distances from the tip to see if there is any effect as we get closer to the end of the applicator, for specifically for systems that have an overdrive feature where, for example, the source is slightly sent over to a position above what is programmed and pulled back to reduce the snaking effect. So in those situations, there can be inaccuracies when one is too close to the end of the lumen. So here we're testing the distance, this offset that we get from the tip to the center of the first radiation point. And we can, based on the program point, we can see if this is within 1 millimeter or so. Now, this was done with an older technique when we had a CT sim in the room and we had film that we can develop. But one can use a basically GAF chromic with actually LINAC radiation to also do double exposure, as I'll show you, if one sandwiches it in between solid water. Now, once this is done, this whole process, so you would want to have your commissioning worksheet, list the model, description, and your nominal values for your offset, which is the center of the source to the outer wall. And you want to get the values that you get from your autoradiograph and basically to compute the difference between the two. So here you can see the difference is quite minimal, and in this case you would accept the applicator, at least regarding the source positioning, given that it's plus or minus 1 millimeter. Now, if it's higher than that, then we have to go into how you deal with that, either by investigating if there is a defect or finding if this error is systematic in a way that can be systematic and reproducible in a way that can be taken into account during the treatment planning or delivery stage. One thing to be very careful about is that although we have some of these spreadsheets with different models, the offset will be different based on the applicator you have and based on your source geometry. So this is something that you have to be very careful about to have the correct values for the nominal values, and it's very specific to your applicator and to your source. So very important that you know the design of your source to know, for example, this distance from your tip of the source to your center of radiation, which will be used to calculate the offset. So in this case, it's 0.35 cm, and we'll show you how that can get implemented. Now, sometimes double exposure is preferred, where you do an autoradiograph and then you also expose the film at the same time, so you get the shape of the applicator with the different duals superimposed on the same film. But I realized that you may not have an imaging system, so this is an alternative way to do this. This was done for a few tandems, and you can see that basically instead of the imaging, we have an outline of the tandem, and then you have the different locations. So it's not an as accurate method, but it's something that can be done as a substitute. Now, going forward to making the...
Ben, can I stop you just for a second?
Yes, sure.
So I think we'll just take a minute and see if anyone has any questions over offsets, because that's quite an important topic, and Ben covered it in a lot of detail.
With the offset, I'll have another section to go into that. But yes, that's a very important, probably the most important aspect of the commissioning. So does anybody have any questions regarding this?
If you have questions, feel free to text them directly to me or to Rayos Contra admin, and we'll be happy to answer those. And just to reiterate one more time what exactly the offset is, it's for a given position. So when you send your source to a given position, the manufacturer will specify nominally where it should be relative to the applicator. So typically for things like tandems, the manufacturer will specify how far that particular source position will be from either the inner lumen of the applicator or maybe from the outer lumen, from the outer edge of the applicator. But the manufacturer will specify some distance relative to the geometry of the applicator of where that particular source position should be. And then you actually measure it by typically an autoradiograph is described, and you then see if that measurement agrees with the manufacturer. Okay, just to reiterate that key point. So again, send us questions throughout, and know if you have a question, probably a lot of others do. Okay, thanks, Ben. Continue.
Please feel free to stop me at any time. The one thing I must say, I'm not monitoring the text messages that are coming through. So Adam, if you see a question through that, just let me know.
Sure, problem.
And I'll continue. So yes, this is what Adam was mentioning. This is what you're expecting as far as the center source to the outer, center of the source to the outer wall. And you will be performing the test to basically see what the accuracy of that positioning is and if we are in tolerance. So we went over this.
And we have one
Sure.
question. You can go ahead and answer now if you want.
Go ahead.
Any specific recommendation on radiographic technique for autoradiography, dwell times, types of films?
Yes. I'm going to skip to that point because that's a good question. Let me just find in my slides where I put that. So this will be one technique that can be used if you don't have a radiographic system, but you have a linear accelerator and you have GAF chromic film. What you can do is to place the applicators and the film under solid water slabs, and in a LINAC, for example, put it at 3 cm or close to the Dmax and deliver 1500 mu. And you can check that you can check the film and to see if you're getting enough of a signal to give you a good radiograph of the applicator, and then one can deliver the HDR plan to get a double exposure for the autoradiograph that goes. Now, in the case that you don't have it, was what I was trying to mention. Let's just say you have film here. You draw what an applicator outside should be. I mean, there's some variance in that, but you try to do it as best as possible. And you have applicators basically taped onto this chromic film, which could be EBT3. Here is an older version of the EBT, and you do the delivery. Basically, when I do it, I basically do 1 second deliveries, which usually gives enough of a signal, 1 second to 2 seconds on each of the dual positions, and that will give you a good signal to be able to detect the center of the radiation. But that's one technique. So one technique, which is the crudest one, is to physically draw where the end of where the tip of the applicator is. The better option is to do a double exposure if you have a radiographic system. It could be your OBI as well. It could be used if you have a linear accelerator. Or you can actually use the MV beam to get a double exposure if you put solid water and deliver enough MUs. So those are the 3 techniques.
Thank you. That's
Yeah.
actually a really interesting idea with the solid water. I actually haven't used that before, so that's very helpful.
Yeah, we had the same issue because our simulator went down, or we took it off, and then I'm like, how am I going to do double exposure? So that's actually from a paper that Robert and Stern had, and that was her setup. But it's similar to what we've done as well. So.
Ben, we have three more questions.
Sure.
2 of them I'll just answer quickly. What is your action if you see a large difference? So Ben mentioned earlier, you should have plus or minus 1 millimeter. Now he and Claire and I will discuss also that you'll see some bigger errors typically with rings, and there are methods for accounting for that. But in non-ring applicators, if you see a larger difference in one applicator and not in the others, you should send it back to the manufacturer and ask for a new one. If you have systematic differences, then you can account for that in your planning system one way or another, and you'll see in particular on rings how that's done. Another question, in which kind of applicator is it important to measure offsets? That would be in all applicators. All applicators, you have to measure offsets. And one more question, I'll leave this one for you, Ben. Why is the offset important?
Oh, well, offset is, for HDR, the most important thing, obviously, well, the 3 most important things. So what is happening in HDR? A source is moving to a specific location and dueling for a certain amount of time to deliver those, right? So most important is our positioning, and positioning can be different in different applicators because they have different diameters relative to your source. For example, for applicators that have bends in them, there's different ways that your afterloader will try to maneuver in that, depending on your system, there may be issues with that. And there are some applicator specifics, such as a ring applicator, which shows large deviations. And essentially what the goal of this is for you to have confidence that if you're using a certain applicator and you send a source to a programmed position, you will get that position plus or minus 1 millimeter, at least within that tolerance. So it's very important because everything in HDR is positioning of the source, right? So if there's an applicator that we know systematically is given a different offset, means that you're sending it to a location, but it's going to a different location. Let's say it's going to a location 3 millimeters above what it should have gone, then that's a big systematic error that you have to address in some way. Yes.
Oh, go ahead, Ben.
We'll go into that portion where you have to address it. But for most of the cases that you have, you're just basically testing to see if it's within 1 millimeter.
So I'll elaborate on one important point. So the offset allows us to know where a certain dwell position is. Typically, the most distal dwell position is relative to the applicator. So when we're looking at our treatment plan and we're looking at a CT, for example, with a tandem, for example, inside the patient, and then when we put on our electronic first dwell position, you can measure with the ruler in the TPS from the outer edge of the tandem that you can see on the CT to the center of the electronic source position, and that should agree with the value that you commissioned. So that's I think one of the most important concepts of the offset is to see that on your CT of your patient, that the first source that you've put in, your first treatment planning source, is in the correct patient, is in the correct position.
Right. This is a slide that was coming up a little bit further, but essentially it's kind of going over the same thing. Here we have a series of sources in the treatment planning systems that are on, which is the green, and off, which is the red. And we're looking at the most distal dwell, as Adam mentioned, and we're looking at the center of that. And we can determine based on the geometry how far this distance is and how far, what is our accuracy in that. And just following up on visually what Adam was saying. Now, the applicators are not by themselves. So the transfer guide tubes that connect the afterloader to the applicator actually play quite an important role. And the use of the applicator should not necessarily be separated from the transfer guide tube. You can think of them as one coupled system. And due to that, when you're doing applicator commissioning, you also need to determine the transfer guide tubes that are going to be connected to it, and then determine if you have a variable length system, a system where you can have different applicator transfer guide tubes with different lengths, such as the Varian Varisource. We would want to document what should be the nominal lengths for nominal internal channel lengths for the coupled applicator plus transfer guide tube. Or if you have a fixed system, is that you're using the correct transfer guide tube to give you, let's say, 130 cm for your measurement. Now, what I like to do is label the transfer guide tubes at both ends. And if they're specific for an applicator, for example, you see on the left here that you have three transfer guide tubes connected, and this is for tandem and ovoid. So we label them T1. That means tandem, first channel. Our right ovoid is always number 2, and left ovoid is number 3. So, and you want to label these at both ends so that it can be connections can be verified. For interstitial, you can see here we have one just numerical 1, 2, 3, 4, 5 up to 20 that we have labeled. Now, what you see on the right is our measurement tool. It's basically a wire that will send through your transfer guide tube through to the end of the applicator, and then you can make a measurement of what this internal length is going to be, and that will be used in the treatment planning system. There are some caveats to this and some things to be careful about, specifically, for example, for the Varian system that I'll go into in a bit. Once that is determined, then what you want to do is some delivery tests. So these are different applicators. So on the left, you see a bunch of needles. So whenever we get a new inventory of needles, we connect all of them. We measure the internal length, and we send the source close to the distal end of the applicator, and basically see if both the dummy in the afterloader and the source can clear and go to the specific locations. So that will give you another functional test, which is your delivery test, to make sure that these applicators are deliverable. The one word of caution that I wanted to give, and I hope I don't confuse people here, it's very specific to the Varisource system, but it's something that causes a lot of confusion with people. and I wanted to mention it. The Varisource system is designed to such that in treatment planning system, one gives the internal length of the transfer guide tube plus the applicator. But for them to connect to the turret, there is this metallic portion that kind of sticks out, that's 1.4 cm, which they do not consider as the internal lumen. So what happens is that when you have a measurement made by putting your wire through this and making that measurement, you will also measure this additional 1.4 cm. However, when you are doing the treatment planning, the TPS will look at the internal lumen length of your applicator for a transfer guide tube. And the way of doing this measurement that inherently incorporates this 1.4 cm has to be corrected. So here you see a bunch of different applicator tandems that we have. When we do the measurement, we send the wire here. We know that there's this metallic 1.4 cm and then the internal lumen. We know that the measurement we get is 1.4 cm more than what the internal lumen is, and we have to correct that to be able to for the treatment planning. This is also one other reason that you want to do the autoradiograph and measure offsets, because this will tell you that you're at least programming the right location for your dual, taking into account any adjustments to the measurements that have to be made, such as in this system. So that's one thing that you should be careful about it when coupling transfer guide tubes and coming up with the nominal internal lengths. What we do is in our clinic, we'll have a spreadsheet at the treatment planning area, which will tell the therapist, okay, if you're measuring a tandem, your measurement should be 114.4 plus or minus 3 millimeters, including that tip that we have during the measurement. But your treatment planning, which is set over here, is 1.4 minus that, and that is what you include in your treatment planning system. So what you need to do is understand exactly how the TPS models your applicator plus transfer guide tube, and understand how one is making the measurement. Specifically, because we're putting a wire in this way, we'll go through the 1.4 cm that we have. So that's a word of caution. As I mentioned, I found it very useful that from this commissioning process, one comes up with a general guideline that we put in the treatment planning area just to remind everyone what, for each applicator, what is the dead space, what is the nominal measurement of the transfer guide tube plus the applicator. And you want that because the biggest sources of error in HDR is programming the wrong location. So we've had situations where the therapists are measuring the internal length, which will be used for treatment planning system, but for some reason they write down the incorrect length. And if the planner is not aware that there are nominal lengths that should be for the transfer guide tube plus the applicator, then there's a potential for error. So this is something very useful that definitely should be communicated to the team. And in general, even if you have a fixed length system, you want to always measure the channel length with the transfer guide tube to connect it prior to delivery, just to make sure that you have the right length for your parameters in your treatment planning system. Now, in addition, for the treatment planning, so we're talking about the parameters that you need. In that sheet, you want to also list any offsets. any systematic offsets that the specific applicator has. And we'll go through systematic offsets and how one deals with that. But for the planner, it's important to know that if it should be planned with an offset, it should be delivered with an offset. So these are things that should be clearly communicated because they're really the largest sources of error. Some person commissions it, but it's different from the person who's planning it, and this knowledge has to be transferred through. One thing in the commissioning process, if you want to use solid applicators, you need to essentially go through the process of commissioning the solid applicators as well. And that really depends on how you're getting your applicator set up. So a lot of the treatment planning system already have these templates for solid applicators built in. Now, one has to verify that those coincide with the applicators that you're intending to use, because it may be a different geometry. It may be that in the template, one is not aware where the channels should be starting, and one needs to make sure that coincides with the physical applicator you have. So here, this is a Miami applicator, and we have a solid applicator template here. One thing, for example, we want to check is you get the applicator here. You want the dimensions to be correct. More importantly, you want to make sure that the channels correspond to each other for the template applicator, and this can be done by superimposing the two onto each other. Once this is verified, once the parameters that come in with the template are verified, then that could be used as an aid for the treatment planning process. The best way to do this is to take a CT of your applicator, have your applicator template in your treatment planning system, and look at the coincidence of the two. If you don't have solid applicators in your treatment planning system, they do allow you to build your own, and that's something that could be followed as well, because these are the solid applicator templates can be quite useful. Now, for some of so this was an interesting thing we did. So we had a solid applicator here, template here, where we printed it out on 100% scale, just using a printer. And then we had a treatment plan where we had duals enabled every 2 cm and a specific dual at the tip to determine this offset. So we're determining the offset from the printed template here, and you just have to make sure that it's in 100% scale. But this is one way to kind of combine the autoradiograph with the solid applicator template that you have. Here, just note that we didn't deliver this with the applicator. We just took the central lumen and aligned it with the printout of where the dual positions should be. And then we can measure the offset, we can measure the center, the first dual to the end of the lumen, and verify that these are all correct. Now, commissioning doesn't mean that one just looks at the applicators, makes sure that they're functional, and makes an inventory, and that's it. Commissioning, big part of the commissioning process is training of staff. This is really, really important because usually the person who commissions it may not be involved in the implantation process, may not be involved in the treatment planning process, and these have to be communicated to the staff in order to prevent errors. So training of associate staff for use of applicators. So you want to get your physicians or therapists that are assembling the applicators and go through hands-on sessions where you show them exactly how each component is assembled, what each component is. You want to talk to the therapist about how to take care of the applicator so there's no damage. And this also includes taking care of it, for example, dedicating specific sterilization boxes to it and coming up with a specific procedure for either sterilization or disinfection. Now, it would be good to develop instructions for clinical use so that if the staff changes, that there's clear documentation on how the applicator should be used. And this also is the part of the commissioning process that has to be done just an equal footing with the physical measurements that we do. Sterilization is an important component. Usually you go to the manufacturer guidelines, and here, for example, they give you different ways that it could be sterilized or disinfected. Normally, applicators have a limit on the number of times that they can be sterilized. So at this point, you want to create a log that every time you send the applicator up for sterilization, that you basically record that, and you record the number of times the applicator is sterilized and used to see when you come up to the life of the applicator and when the applicator should be ideally replaced. Now, sterilization is not easy. We've had many situations where, they've been incorrectly sterilized. We've had damage because they sterilized with a technique that with a thermal technique that should not been used on the applicator. So this has to be very well communicated to the folks that do this disinfection and sterilization. This slide I'm going to skip because this is a little bit more complicated. This is for modulated applicators or shielded applicators where, for example, here you see cylinders where, for example, you can put a rectal block in them. Now, the problem with this is that if you're using TG43, this is not modeled in there. There are algorithms such as Accuros that allow you to do inhomogeneity corrected dose calculation, but they're not really used in clinic. I don't believe that this group will have an opportunity to use these kinds of applicators, but in case that you want to use them, there is a little bit of description on how one can do measurements of the attenuation and how one can make this modeled in the TPS. And if you guys want more details, I can go into that, but I just don't believe that in most places this will be used and may create confusion. So again, going back to what was recommended by the task group, there's, if you look at the frequency in the tables, there's two things that are listed, initially and annually. So initially means that initially when you receive the applicator and you're doing the commissioning. So it should be, you can think of it as commissioning, and then you want to have an annual QA procedure that builds on this commissioning that essentially goes over the guidelines that should be done annually. So for example, applicator integrity should be tested annually. And here, basically, I've outlined the ones that should be tested annually. And part of the commissioning process is to develop an annual QA spreadsheet process and also determine when the annual QA is going to be done and how basically the quality assurance is going to be handled moving forward. Now, with the time that I have left, just to go into an example, which will be elaborated furthermore by Adam and Claire, is the case for ring commissioning. And this is an interesting case because it's actually very instructive and it shows what happens when things are not as one would expect as far as the positioning goes in the applicator. So it is common to use tandem and ring applicators. They're easier to implant than tandem and ovoid, so there's many institutions that use it. However, the commissioning is quite tricky. It's been shown that the source dual positions in the ring applicator deviate from the intended position by up to several millimeters in some applicators. Now, this discrepancy due to relatively small size of the wire to the ring lumen, causing different possible paths, as well as the afterloader maneuvering through tight curves. And it's important to quantify this offset versus the intended position of the source that one would expect if there was no systematic offset. Yeah, there are other reasons that these offsets differ. It could be wire diameter, the stiffness, number of different aspects that contributed to this error, systematic error. So experimental setup is similar to what we talked about. You want to take your ring and position it so that it's flat on your film, tape it down, and you ideally you want to do a double exposure, but here, for example, you deliver your treatment plan, which is a number of dwells across the ring, and basically one tries to measure the distance of from the tip of the applicator to the center of the radiation source to get the offset and compare that to what one would expect if there was a perfect positioning of the source in the applicator. You want to perform these tests several times to make sure that it's reproducible. Specifically, if you see a systematic error that needs to be accounted for. If the error is intermittent, then this will come up when you do the test several times, and it may lead to a different way of dealing with it and incorporate it into a treatment planning system. It may be defective, for example. If you don't have a radiographic system to do a double exposure or a system to even develop the film, if you have that anymore, this is what you can do in a LINAC. Basically, you want to put buildup of water on top, put the rings over film, and expose the gaphromic film to a much higher level that you would with the megavoltage beam. So here, what was done is 1500 MU under 3 cm of water with some backscatter. And what you can see is that you do actually get a good image of the ring. And then once you deliver the HDR plan, you have the source positions superimposed by that. So that would be a really nice way to get a double exposure autoradiograph. And then there is some imaging software that are free, such as ImageJ or Fiji, that can be used to do the analysis of the delivery. So what we talked about how to get this autoradiograph. Now it's basically how do we do the measurements and how we determine what the offset is. Here the example is obviously we're on a circle, so the distances that we're going to calculate are based on the arc length. And here, for a case where the sources or the lumen is 130 cm, one can move back a little bit because there may be an offset that's towards the distal end of the applicator, and you don't want to be hitting the end of the applicator. So you can start at something lower than that. If you have then once you deliver that, what you can do is the positioning of your dwell is going to be, let's say, if you sent it exactly to 130 cm, or that's the distance of that is the length of your internal lumen. You take that, you take your arc length, and you subtract the 0.35. Now that 0.35 comes from your geometry of your source. And it's very important here to note that if you're using a different source that has a different geometry, that distance that is the distance from the tip of your wire to the center of radiation may be different. So just to clarify this 0.35, I'm going to go back to what we had as far as the diagram of the offset goes. And basically what we're looking at is you want to get the diagram, technical diagram of your source, and you want to know, okay, tip is here, which is the program position. The center of the duals is here, and that gives me 0.35 cm or 3.5 millimeters. And that's what we're taking into account. So these are examples using a source like that, but please be aware if you have a different type of source, these values will be different for example, for this equation that you see here. And then you can get your delta or offset for the exact dual position, that's the nominal dual position that's from your plan, subtracted by the actual dual position. And that will give you an offset. Now, you can repeat this for a number of dual positions. Typically, the most distal dual is the most important one that we looked at, but these can be quantified for all the duals that we have there. Once we have that, we see something very interesting, in that for this type of applicator, there is really a significant deviation of the offset from where specifically the difference between the planned position and the position that the wire will be at for the specific applicator in that plan. So in this case, what you can see is a few different rings, 30, 45, 60 degree ring, and offsets were measured. So this plot is the program position minus the measured position. Measured position being the position that basically is dependent on the applicator, program being ideally what you want. And here, what you see is that you have a large variability, your positioning, especially towards the end of your applicator. And if you do basically a weighted average of them, you can argue that this is basically a deviation of 0.34, which is, for the treatment planning purposes, we'll round down to 3 millimeters. So 3 millimeters is quite a bit, right? Compared to the plus or 1 millimeter that we said was your tolerance. So this is out of tolerance. But the question is, what do? Do you return it to the manufacturer? And it turns out, okay, return it to the manufacturer, get a different one. All of the rings, for example, for this Varian system, will give you a systematic offset. So it is not necessarily due to a defect. Once we see that this offset is reproducible, so we do this experiment multiple times, and we see that we get approximately 3 millimeter off. Negative means that it's towards the distal position. Then we have two options. We can say, okay, if I plan it normally, what actually will happen is that the first source position will be 3 millimeters further down, right? So the simple thing is that, okay, I plan it, ignoring that information, and then when I want to deliver it, I move back everything 3 millimeters, so it corresponds, so the delivery corresponds to the plan. It's a little bit confusing, because whatever you planned, your source is going to go 3 millimeters past that. So when you're at the afterloader trying to deliver it, you can edit the channel and move 3 millimeters back. The effect can be, so this is basically the two alternate methods. What I described is the delivery, doing it through the delivery system, through your controller. The other option is to incorporate this in the treatment planning system. So just before we go further, I was showing this graph on the left where we have a 3 millimeter offset from the actual planned position. And here we can correct the data by shifting everything 3 millimeter. And then we'll see that we're kind of within that range that would be acceptable for variation. So this is a different way to deal with this offset, is that you deal with it in the treatment planning system. So instead of putting the tip of your applicator at the end of the lumen, in this case, one would basically, during the planning process, extrapolate the position, your source position, 3 millimeter beyond the inner tip. Because that's really what's happening, right? If we send it to a specific position, it's basically 3 millimeter higher than that. So if you want to verify this in your treatment planning system, you actually make this shift in the TPS. Once you make this shift, then the dosimetry will be that you're visualizing would be accurate, and you don't have to do the shift at delivery system. So you do either or, you don't do both of them. You can either say, okay, we're off 3 millimeters, we're going to shift it at the controller, or you say, okay, I prefer to do it in the treatment planning system, and I'm going to move where I put my channel by 3 millimeters, as it's done here. Let me see if I have, yeah, I don't have much more. Now, those are two ways of dealing with situations where the offset is not as expected. Once that's determined, you want to come up again with a policies and procedure guideline that shows for your clinic, what are you going to go do in this case for this applicator, right? And that's, again, something that has to be disseminated to everybody who's planning these cases. You want to document your results. Here we have basically a couple of examples where we have our planned position, the displacement, and we have the difference, and then we have the dual for each ring applicator after the correction has been applied. So once you come up with this correction technique, you want to make sure that basically, once it's corrected, the positioning is accurate, or so within 1 millimeter, as shown here. Now, as a final thing, you want to have a commissioning document. And this is an example from Sonia's group at UC Davis that indicates the components that we went through, right? For example, physical inspection, that passed; radiographic inspection, that passed; length measurements passed, and things like that. You want to have the part lot numbers. You want to attach instructions of you, document which test has done, and then develop a tracking sheet where you can basically track how many times these applicators have been used, to check that they don't go beyond their lifetime, their sterilization, and things like that. So that's the basics of it. I'm going to end with some references. So these are, the first set is basically general references on guidelines for HDR and applicator QA. The second two are really interesting papers. Obviously, the one by Robin Stern, which was on the ring applicators, quantifying the offset and the techniques to deal with it. And that's basically what was shown here. And there's other papers that go into more detail in the commissioning of the ring applicators. Now, to my understanding is that Adam and Claire are going to follow up on this next time, right? With more detailed hands-on videos, right?
Yes, we're going to elaborate for one full section on rings, because they are quite complicated, and we're going to discuss step-in systems, so those like used by systems like Nucleotron. We'll talk about stepping out systems like Varian and Eckert Ziegler and Babig. So we'll discuss in detail all the complexities. But this was a very good first presentation of the rings.
Right. Thank you so much. I really wanted to thank the people who I have here. I'm I'm only contributed a very small part, but we have some heroes here that I know. Adam, for example, for many years has been on this project and has been helping out with Radiating Hope. And I'd like to also acknowledge Sonia Dietrich, who contributed some of the slides here and is one of the educators in this program. And give a shout out to Benjamin Lee, Betty Chang, and Claire Dempsey for all their help. Thanks, guys. Any questions?
Thank you very much, Ben, for a wonderful presentation on applicator commissioning.
Thank you, Adam.
While we're waiting for any other questions that are written in, I'll ask one question to you. So I know at least one or maybe a few of our centers are just installing HDR systems and don't have the active source yet. They won't have it for maybe a few weeks or even a couple months. Which tests would you do now for your applicators before the source arrives?
So, yeah, that's a great question. And there are important things that you can do, right? If we go kind of at the beginning, obviously we won't be able to do the autoradiographs or anything like that. But what we be able to do is the visual inspection, right? To create an inventory of your applicators that you have, test the integrity. If there's any issues, send it to the manufacturer or acquire a different one before your system comes in. What you can do is assembly test. You assemble it, you connect to the transfer guide tube, and when you don't have the afterloader to test the system, instead of the afterloader, you're going to take a wire and basically feed it through the applicator to make sure there's no obstructions or things like that. So that'll be your pseudo delivery test. So functional tests can be done. If you have an imaging system, you can look at the internal structure. You can also look at the dead space, which can be quantified. And then the rest will be dependent on the source, right, and the positioning. And so unfortunately, that part will not. You would have to wait until it's received. But essentially, you can do the visual inspection, the functionality test, the inventory, and if you have access to the imaging, and do some of the imaging that goes along with it. You can do, set up your solid applicator templates or see what you have. But unfortunately, for the treatment planning and the delivery and the actual the part of the commissioning that really heavily affects the quality of the treatment delivery has to be done with a source there, because you have to quantify the whole system, applicator and transfer guide to your system, to be able to get the correct values, for example, for the offset for the ring applicators.
Great. Thank you so much for that answer. And I don't see any more questions written in. Again, if anyone has any questions over this presentation, feel free to email Ben directly. You can email me. You can email Sanja as well as Claire, and we'll be happy to answer those as soon as we get time. And again, just to remind you, we have another presentation tomorrow at, I think, the same time. We'll send out a confirmation email along with a presentation that you can review before we start. And again, this will elaborate on ring commissioning for multiple systems, including step-out systems and step-in systems. So thank you very much again, Ben, for your time.
You're welcome.
And
You're welcome.
wonderful presentation.
You're welcome.
And we'll talk to everyone tomorrow. Thank you.
Thank you, everyone. Bye.
Thank you. Bye. Good night.
Good job, everyone. Good night.
Okay, good night.
Good morning. Okay.
I have good night now.
Yeah.
Okay, bye-bye.
Bye.